let's move on. So today we'll be talking about basically how do we implement networks, number one, the concept of layering, number two, and focus on OSI and TCP/IP. OSI and TCP/IP being the actual number one standards when it comes to implementing networks, you know, and this is very important. I'll talk about it. Why do we need layering? What's the concept behind it? And obviously, this is going to be the foundation of any networking program, application, system, design that you plan on doing in the future. Because without understanding the concept of layering, you probably would not understand the concept of networking. So the first 4 weeks, you could see we kind of introduced the subject, to be honest, in 4 weeks, but not introduced in generic terms, in detailed terms, the idea of the physics behind it a lot, you know, and the performance behind it, the metrics behind it, the communication media behind it. Now we want to talk about how do we implement it? How do we put all these together in a specific networking environment? So let's start by saying we need abstraction. Of course, we need to hide the software from the hardware. We need to abstract what's happening behind the scenes. And that's what we refer to as software abstraction. So linking the software with the hardware, obviously every networking environment has a software and a hardware component. So when I have a router, what makes this router do its magic, obviously, is the abstraction of the software. You know, the function calls of the software on the hardware itself, the APIs that we have, the SDKs that we have that allow us to use this hardware. So yes, we need abstraction. Obviously, an example would be operating system. What do? Is we divide and conquer. We say, okay, we want to send a message. Let's divide and conquer this. Let's divide it into pieces and conquer each one separately. And that's what we refer to as divide and conquer. We use the concept of layers in order to do the divide and conquer. Layering meaning every layer is a class. If you've taken programming, object-oriented, every layer is a class, and every class has its own functionalities that it's supposed to do. And when it's done, it feeds. It has input, and the output of that layer is an input to another layer. And that's the concept. On one end, we go down the layers. On the other end, we go up the layers. And this is the kind of thing you want to kind of engrave in your head somewhere, okay? So layering is very important because it allows us to access the hardware, allows us to divide this big, huge, complex problem into smaller pieces where each layer is in charge of a specific functionality. That's the basic idea here, okay? So we send specific amounts. Again, we have complex services to look at. So again, this is the concept of layering. So as you could see, we have multiple layers. This is a simple example. As I said, typically on one end, we're going down the layers. On the other end, we're going up the layers. And every layer is doing something. Again, think about this as a sender. And think about this as a receiver. Okay? Okay, so the idea is on one end, I'm going down, and every layer on this side is doing something with my message. So obviously, I have a message, and every layer is doing something to that message. It could be adding a header, adding a tail, adding overhead, adding a checksum, modifying some stuff with it. You know, we're doing that so that we understand what I'm doing with the message on the other end. So this is a virtual communication, as you can see. We have abstraction, meaning there is an interface between these two, but this layer doesn't know how this layer did what it does. All it knows is it gave me an input. I'm going to take that input, do something with it, and give it to layer one until I come to the physical medium, which could be a cable here, or it could be wireless, and it moves until it comes to the next router, switch, whatever that is, and does it again and again. So this process is being applied over and over again. Obviously, between the sender and the receiver, in between, we have a lot of things happening. So keep that in your mind when we're looking at something like this. Layering is important, allows abstraction, transparency. We have protocols, as you could see, protocols and interface. This is what we refer to as a protocol. What is the protocol, be quick? What is the protocol? What's the idea of a protocol? If you want to define a protocol, what is it?
It's like a set of rules.
Set of rules. Excellent, excellent. Thank you. So these are rules that these sender and receiver agree upon. We have many examples of protocols out there. Again, TCP is an example, IP is an example, HTTP is an example, FTP is an example. All these are protocols, you know, people have designed to allow the sender to understand or to communicate with the receiver, or the receiver to communicate with the sender. Okay, so that's the basic idea of a protocol. So let's move on. So again, a lot of example. You have here 5 layers. You could see protocols between the layers. So this is again virtual communication. What does it mean virtual? Meaning it's not actually a link between them. There's no link, but virtually they're connected to each other. Virtually, because there are a lot of things in between that allows them to connect. Okay. Obviously, within the same host, you have interface. Again, the idea of the interface is making layer 5 give information to layer 4 that they would use without knowing how it was done. That's what we call interface. And obviously on the other end, we have also interface backwards. That's why you could see this arrow is bidirectional. Why is it bidirectional? Because if you're sending, typically you're going down. If you're receiving, you're going up. That's the basic thing. And what are these guys doing? One more time, I have a message. This is my message. Again, I'm Googling. I'm sending WhatsApp. Hello, how are you? I send a smiley face, right? If I send a smiley face, that's my message, a smiley face. What happens to it? It goes down the layers. So here, it's going to be a smiley face, okay? The same smiley face. However, I will add stuff to it. This layer would come and say, you know what? Let me add some text. We call it, suppose, L4, layer 4, overhead. Okay? Or I will add something before it as well. The sender, receiver, stuff like that. Then it goes down, same thing. I have my still smiley face, and I will add stuff to it as well. So, for example, and then we go all the way here. So I have my smiley face still, again, in binary, of course, with a lot of things added to it by these different layers. And again, with other things happening. So could be for encryption, for example, at an application layer level. So when it comes here, what do you think happens here? What do you think happens here? Yalla, bonus point. What do you think happens here? What do you think happens here in layer 1 going up? What do you think happens here? Come on, guys. No, what you guys know? Signals.
Conversion.
No. What do you think happened to this guy here?
It turns into binary codes.
I mean, obviously it's binary, it's a signal. I mean, yes, of course, it went through the physical medium, it came here. What do you think happens when we're going up? Come on, come on.
People are saying it gets decrypted or the data is sent.
What's that?
People are saying it gets decrypted or data is being sent.
No. Come on, guys. Here, look what happened. Look what happened here. What do you think will happen here? Look what happened here. What will happen here?
The same thing, the opposite.
Yeah, what?
Loop.
Conversion.
Layer will do what? What will every layer do?
It will almost send the messages.
Translate.
Yeah, just almost translate the messages.
Yeah, translate the message.
Okay, Muhammad Deep. Okay, what, Muhammad? Good. Obviously, come on. Here I'm adding. Right? What would I do?
It deletes. It deletes.
You would remove. I mean, come on.
Separate.
You would read it. You would look into it. You would look at what they added. Understand it because you have a protocol. Do whatever you're supposed to do, whatever this guy told you to do, and remove. So the smiley face that started here like this, the smiley face that started here with a lot of things, as it goes up, these things will be removed from it. Okay? until I get what here? The last layer, what would I get here? What would the message look like? Bonus point from Muhammad Deeb. Okay, Brooke. What would it look like here, my message? At the layer 5, for example, what would it look like?
Words or smiley face.
To be only smiley face, only, without anything with it. So that's how, when you sent a WhatsApp message to your friend, a smiley face, he got a smiley face. What you don't know is that smiley face went through a lot, guys. It went through a lot. You know, layering after layering after layering on your phone until it left, until it went through a whole bunch of routers and switches, until it got converted to signals and electrical waves, until it came to the tower, until it got forwarded, and then finally they get the smiley face. Okay? And you can see it's so simple. It takes a microsecond. You go to WhatsApp, say, hey, what's up, guys? This WhatsApp, guys, it's really going through a lot. That's why people say, you know, using the internet, and they kind of say that, you're consuming a lot of energy. Yes, your computer, your phone is not consuming a lot of energy, but what you don't know is that message is really putting a lot of things out there into action. Okay?
Professor?
Yes.
Is the text the same? It goes through the same concept?
Yes,
Like text message?
file, text, everything. Anything you're sending, Googling. You go to Google.com, same thing. Huh?
Even pictures and videos and stuff?
Everything that leaves your computer is a bunch of zeros and ones converted to signals. So you don't care what you said. This video now, you're watching me, right?
Yeah.
This video is being converted exactly what you saw now. This video is being converted overhead after overhead, live streaming all the way to the other end. Imagine. A million towers in between. Okay?
Thank you, Professor.
I have a
Interesting.
question.
You know, this is so cool, though, to understand this whole concept of networking in a very basic form. And this is what we'll be dwelling on. Sorry. This is what we'll be dwelling on in the next 5 weeks. You know, we're going to go zoom into this whole concept. Okay? Any other question before I move on? Don't worry, we'll be talking about it in details, but I wanted really to spend, you know, to go kind of pause for 1 second and look at this and imagine, well, how are things happening? And if you're taking programming, CSCI 124, 111, and even if I taught you, so you will understand this more obviously when you do object-oriented, but the idea is this doesn't have to do, but it's very similar to the whole concept of object-oriented. How many layers can there be? Very good question. Typically, there are standards. You could define your own networking up to 2, 3, 4, but obviously if you're using TCP/IP, which is the internet, it has 4 layers, you know. If you're using OSI, it has 7 layers. We'll be talking about it. Or using a combination between both, it will be 5 layers. So it depends on what standard you'll be using. But if you're using the internet, basically TCP/IP, you are typically using 4 layers. We'll be talking about it. But good question. 7 layers if it's OSI, which we don't use. OSI typically is obsolete, but we use it for teaching because I'll tell you why it kind of died and TCP/IP took over. However, you could use any networking concept. You could build your own networking concept. And if you want to build it, usually we use it, we build it based on the OSI. Okay? Very good. I love it. I love the question. Let's move on. So let's go over protocol stack. Again, this is what we call layer N protocol. Again, what we saw now was a layer 5 protocol, layer 4 protocol. Obviously, how many layers do you have? N is how many layers do you have? And protocol stack, as you know, you saw it, it's like a stack, right? We're stacking protocols on top of each other. That's why we refer to it as a protocol stack. So what is a protocol? Again, we've talked about protocols before. It's a set of rules. It's an agreement between the sender and the receiver. So for example, we could have a protocol and say, you know what? If you want to ask a question, in this session, put your hands up or write on the chat. This is a protocol. If you apply the protocol, therefore, I would listen to you. If you don't apply the protocol, I will completely ignore you. Okay? So therefore, this is why it's a protocol that me and you need to agree on. It's kind of a handshaking. That's what we refer to as a protocol. I could give you another example. Again, like translating. Analogy to it could be, again, protocol of shaking hands. You know, like in some countries, they don't shake hands, right? In Muslim communities, you don't shake hands, for example. If you do that in America, in another community, it would be an insult, right? If you go to a meeting like, oh, you're not shaking hands, you think you're better than me? So it depends on the protocol, it depends on the culture. In our case, obviously in networking, it depends on the protocol that we're using. So that's the whole concept of protocol. It's an agreement between the sender, you being the sender. If you go to google.com, you're sending something, that's your protocol. You'll be using HTTP, for example, to browse. You'll be using FTP to upload files. So that's the protocol you'll be using, okay? That's the logic behind protocols and networking in general. So obviously, when you're a network designer, you're designing a network, you need to agree on how many layers do you need? Do you need 7? Because some of you asked this question, I loved it, because you asked it. Who asked the question? Yeah, bonus point for you. Sometimes asking a clever question shows that you are into it. You're with me. Whoever asked the question, bonus point. Okay? So Brooke, please, if you're with me, give them a bonus point. Okay? Whoever asked the question first. So yes, how many layers is a question that designers decide on? Okay? If you're not using a predefined protocol stack. So you have to decide that. And again, it all depends on how complex your problem is. So if you have like a very complex networking scenario, you say, you know what, I need about 4 or 5, because every layer has its own functionality. And you need to define clean interface. Clean interface meaning every layer needs to understand what that layer is doing and what is it giving me as an input so that I know it. So this is what we refer to as clean interface between the layers. So layers have interface on the same stack, and layers have what on different stacks? Layers have what on different stacks? On the same stack, they have interface. On different stacks, what do they have? Protocols. Thank you so much. Excellent, excellent. Some of you are with me. Sarah, you're very active today. Bonus point for you. Thank you. Okay, so excellent. I love it. Let's move on. So example here. Suppose this is Dr. Watfa, the philosopher's Watfa, not me. Okay, so for example, suppose you are at a specific university and I want to talk to another philosopher, but we don't speak the same language. Again, very similar, right? So I say, أنا أحب ECTE 182. Okay, which is the same course, by the way, I teach at Wollongong, which is networking, but typically more advanced a little bit. So suppose I want to say أنا أحب ECTE 182. If you don't know Arabic, you would not understand أنا أحب ECTE 182, right? Yeah, the guys would not know it who don't know Arabic. So how does it go? So I am in layer 3. So if I want to communicate with this philosopher in MIT, I want to tell him أنا أحب this. So obviously it has to go through a middle person. So I need to have a middle layer, for example, that will have a common ground between Arabic, supposedly, and English, supposedly. And that middle layer, in this case, we decided on Dutch, for example. Okay? So again, it went through Dutch. It was changed to Dutch here. Then we faxed it, we emailed it, whatever that is. The secretary here got it in Dutch. Okay? Was given to a translator who translated it to English. Very good example. Simple, we call it the philosopher, translator, secretary architecture. So this is something you could kind of look at it, okay? So it got translated here, okay? The Dutch translator translated my English here. And then they gave it to the secretary to send it. So this person is the one doing the magic, the translator, okay? So this woman translated it to Dutch. This man took it and translated it to English. So this is from English to Dutch, or Arabic to Dutch, sorry. Arabic to Dutch, and this is from Dutch to English. Okay? Good. So again, this is a very good analogy for you to remember the whole concept that we did. Okay, let's move on. So yes, another example, we have a letter, we put it in an envelope, letter is carried, the letter is delivered, we have some layers, the parcel is taken, the letter is delivered, the letter is carried from the post office, and then it's picked up. You can see this is the sender and the receiver. So I'm giving you a lot of analogies here so that you kind of could remember the whole concept of layer. Let's move on. So when we talk about network architectures, we have a message, as you could see. You have a protocol between them. And as I told you before, when we're going down, we're adding stuff to it. We could even fragment it, meaning I could cut a message, a big message, into multiple messages. Okay, that could happen. So M was here. So I have now M1 and M2. And then I will add headers and tail, head and tail for each one of them. So these head and tail are added by different layers. And then when I come to the other end, you can see what will happen to them. I will start deleting heads and tails until I get the same message. Okay? So this is what we call, again, we have messages. Encapsulation, I'm encapsulating the message in a bigger message with additional information between them. So what's the difference between a protocol and an interface? Be quick, one more time. What's the difference between a protocol and interface? Be quick. What's the difference between a protocol and interface?
Protocol or agreements or like rules. Interface is the process that the message is going through. Like, yeah.
Okay, nice try, Abdullah. No, but not what I'm looking for 100%. So what's the difference between protocol and interface? I've said it before.
Protocol like, but interface like connects layers. Like
The same. Both of them connect layers, and both of them are set of rules. Both of them are a set of rules, and both of them connect layers. But what's the major difference between them? But don't send me private messages, Hassan. You could type it on the public so that if I give you something, it has to be in the public. Hassan, write it on the public, not on private. Okay. You want to write it? So obviously, interface are between layers, set of rules between layers on, as Hassan sent me on the private, between layers on the same stack, and protocol are between layers on different stacks. Okay, and you can see it. This is a protocol, set of rules between layers on different stacks, interface between layers on the same stack. Okay? So yes, let's talk about it. So each layer has these with messages, of course. We do have a maximum size. For example, Ethernet, the cable that you use, has a maximum size of 1500 bytes. That's the maximum size a message can be. So if I have a maximum size, what do you notice will happen? Bonus point. What do you think we notice will happen if I have a maximum size? What will happen to the message? If I have a maximum size limit, what will happen to it?
There will be a delay in sending it.
No, no, Abdullah. What will happen to it? Again, please do not send me private message. Muhammad Deeb.
It will not
like
break into parts.
Sorry?
It will not break into parts.
It will break into parts?
No, I mean it will not break into parts.
No, if I have a big message, it will break into parts, right? Look at it.
Yeah.
They will connect it again before they send it to the receiver.
Yes, so it will break into parts. It's what we call fragmentation. That's what we call fragmentation. And then what do we do here? What do we do here? Going up. If we do fragmentation here, what do we do here? Defragmentation. Thank you so much. Defragmentation. Okay? So yes, a large messages. Why do we do that? Because there are limits. Protocols and interface specify limits. The protocol says, you know what? Like Ethernet protocol, for example, you cannot send more than this for many reasons, which I'll tell you about. Most protocols have a maximum size, like Ethernet, a maximum size, and ironically enough, it has a minimum size as well. I'll tell you what minimum size is. We'll talk about Ethernet later on. minimum size, and maximum size. Okay, and this is very important in the whole flow of the message going down. So again, most of the messages will have a control. Yes, the famous ones, Sarah, the famous ones, yes, you need to memorize them. Like again, the original Ethernet, Wi-Fi, and so on. You do. If I talk about them, you need to know them. Yes, they're very important. The famous ones, of course, not any, but the ones that we use on a daily basis, like Ethernet. Ethernet in a LAN local area network uses an Ethernet. Okay, and obviously Wi-Fi is wireless Ethernet. You think about it. Okay, so messages have a control and a header, and these are used for synchronization, to give instructions, again for security purposes, for message control, error correction, error detection, a lot of things. We use a control and header. Obviously, the data portion is what's important. The data is what is important. Obviously, these overhead are added. So when we are sending, the overhead will affect efficiency and utilization, if you remember, which I've talked about before. Efficiency and utilization. And again, it all depends on the overhead. If I take overhead into account, or if I don't take overhead into account, and that's the difference between efficiency and utilization. This is in a previous lecture I've talked about. Okay, you could go to it. So encapsulation, again, data is encapsulated, meaning every layer, you could see you have layer n plus 1 over it, n minus 1 below it. So if this is n minus 1 is here, and n plus 1 is here. So you could imagine now the picture that we're talking about, okay? So we encapsulate layer n plus 1 message, okay? So I'm here, n plus 1 is here. I encapsulate the message I get from layer n plus 1 in the data portion of layer n. So I take whatever they gave me, that will become my data portion, and I would add to it whatever I want to add to it. Okay, which I gave you like the smiley face example. So you gave me a smiley face, that's your data portion. I take it, and then I would add to it something. Then the guy below me will take what I gave it and add to it something. What I gave it will be the data portion of what they got. Very interesting. And this is what we refer to as encapsulation. Again, it's like a capsule. Encapsulation comes from the word capsule, right? Capsule. Again, what's a capsule? I think we all know what a capsule is. Think about it like a cylinder. This is a capsule. So I'm putting it inside a capsule. So you give me something, I put it here, and I add to it what I want to add. Okay? And then I give it. And they put it in the capsule and so on. That's what we refer to as data encapsulation. Obviously, when we get it to the other end, we strip off all the stuff that were added to it. Okay? So some interesting thoughts when we design layers. I'll put them real quick. Sorry. So what are the things to look at when we're design issues of layers? One is, how do I identify the sender and the receiver? That's the first thing we need to kind of keep in mind, right? How do I identify them? Obviously, we use some kind of addressing. How do I know who the sender is and who the receiver is? What kind of addressing do we use? What kind of addressing? How do I know? IP, that's the most common, right? Typically, IP addressing that I'll be talking about. So yes, I need to give it an ID. The ID is the IP. Again, we've talked about ping commands before, right? So the ID is the IP, most likely. Okay? Obviously, it doesn't have to be over the internet. It could be in a local area network. In a local area network, what do I use? Do I use IP in the local area network? Yes. We use the logical address, right? The MAC address in a local area network. We use the MAC address, okay? Which is also very important, right? So, so we have different kinds of addressing. It all depends what layer you are in. So when I'm talking about sender receiver, I have to keep an idea what layer am I in. Based on it, I would know what kind of addressing I'll be using, okay? So we need to also decide on the rules of data transfer. What are the rules? Is it simplex? Is it one way? Is it half duplex? What is half duplex? What is half duplex?
Basically, like information gets sent, and then you have to wait until like the receiver responds, send again.
Yeah, basically yes. I could send to you, you can send to me, but one way at a time. Very similar to a walkie-talkie, if you think about it, right? A walkie-talkie. Hey, you know, I said, you said. So we're using the same channel for two-way communication, but one at a time. We call it half duplex or a full duplex, right? A full duplex. So again, you have to decide on that. Error control, very important. Why? Because physical circuits are not perfect. So what will happen? What might happen here, guys? What might happen when we talk about error control? What might happen? What do we need to do and what might happen? Come on, we're kind of brainstorming here the design issues, and we will see how people solve these. Over the last 20 years, how people solve these issues. Data could clash. What else? So basically, I mean, in simple terms, let's not make it too complicated, guys. You are sending 000110101. What might happen? Obviously. This is, by the way, encoded to signals like this. This is encoded to a digital signal. We'll talk about encoding later on. This is the signal. What might happen? It could collide, I agree, or it could be interpreted wrong. Instead of interpret the 1 as a 1, it could be interpreted as a 0, right? Which means I get an error. Basically, my message is no longer correct. It could collide, as you said, with another signal, which will make the message incorrect as well. Collide meaning two signals on top of each other. That's what collision means. We'll talk about it later on. So a lot of things could happen to my message. It's not a perfect world. These messages could have a lot of issues. Again, encoding wise, again, circuitry wise, in the communication channel wise, collisions, even in hacking, you know, and so on. People could manipulate the data. So we need to have some kind of error control, meaning I need to have an idea, oh, is the message what the guy sent me? This is so cool, right? So let's think about a quick way to do that. If I'm sending you 1001, one quick way of test will be, is we add to it, again, other than we could have something called the Hamming code and a lot of things. It's simple checksum. Remember, when I'm going down the layers, I could add stuff to it. So one of the layers could add to it a checksum. Again, I'm just giving you a small example. Obviously, they are very complicated, but for you to understand. The checksum is basically sums these. 1 plus 0 plus 0 plus 1. What's 1 plus 0 plus 0 plus 1? For example, again, just to make your life easy, I know we're sending binary, but I'm going to say 2. 2 in binary, that's to make your life easy. 2 in binary. Again, assuming I'm adding 1 plus 1. In binary, 2. So when the guy gets it, the first thing they will do, the receiver, the first thing they will do is check the checksum and see if they added them again, do they get the same result? Okay? If they do get the same result, they kind of feel safe. You know what? Probably the message hasn't been tampered, and the message, there's no error in it. Okay? So I'm just giving an example how checksums work. Obviously, we'll talk about Hamming codes and techniques later on, but this is a very simple way for you to understand that we could add stuff to the message in order to have some kind of error control. Okay? Does that make sense? The whole concept of error control? I hope it does. Okay, let me move on. So order the messages. Another thing is, you have to remember, a lot of people are sending. You're sending M1, M2, M3, M4. Okay, thank you, Muhammad, thank you, all others. I know I could do it in binary. I'm making it simple for people to understand. I said simply 1 plus 1. Supposedly it's 2 in binary. Okay, so no need to put it in binary. I'm just trying to just explain the concept real quick. M1, M2, M3. But thank you, Muhammad, for sharing. If I send a lot of messages, does the receiver receive them M1, M2, M3, and so on? Do they get them in this order? What do you guys think? Is it guaranteed that if I sent you 4 messages like this, you will get them the same order? Is it guaranteed? No. Why not, Sarah? Why not? Why not? It's not guaranteed. Because the messages could go on. Messages could go on different paths. Exactly, on different routes. One message could go this way. One message could go different because of traffic, because of optimal routing, because we're routing the thing, and optimal path could change over time, right? I could have 5 cars leaving my house to Wollongong, and all of a sudden 1 car could go on Sheikh Zayed, and 1 car would go on Emirates Road. So there's no guarantee there, right? So therefore, there should be a way to make sure that when the receiver gets them, that the order is guaranteed. And typically the obvious solution is give every message what? What's the obvious solution? Is give every message what? No, not IP. We'll talk about it later on. So the obvious solution is give every message what? Not an address. We call it a what? Give every message a sequence number. Okay, that's the obvious solution. Give every message a sequence number. So 1, 2, 3, 4, 5. And we need to reset that sequence because at one point in time, I'll be running out of numbers. So that's the obvious solution, but still has issues, which we'll talk about. Please mute yourself. Mute yourselves. Okay, so yes, that's an obvious solution, is give them numbering. So number them basically. Okay, so another issue that we might have, please mute yourself. Also IB. Okay, I need to mute you myself. No, mute yourself. 1 second, let me find them. Okay. Okay, I muted them. Sorry for this. So another issue is, really quick, fast sender, slow receiver. So what would the issue be here? What would the issue be here? No, not decrypt. Not everything is decryption for you guys. Everything I say, I ask decryption. You know, fast sender, slow receiver. Aha, Clark is smart. So we have queuing, right? Now we know it, right? Remember queuing? We talked about this. Because, again, if this is a sender and this is a receiver, this is fast. Sending a lot. And this guy can only receive 1 at a time. So you will have a big queue now. We've talked about it already. So bonus point for Clark. You can't hear me? Okay. Okay. So bonus point for Clark, I was saying. So of course we have queues. So fast sender, slow receiver, we have queue. And what will happen at one point in time, guys? What will happen at one point in time? Obviously, if you keep on sending. If you keep on sending, what will happen at one point in time? We will start, what? The queue is full. Exactly, we start losing packets, start losing data. Okay? Because, again, very similar to what analogy? If I'm a fast teacher and you are a slow learner, what will happen at one point in time? You will start losing packets, right? Basically, the information I'm sending would start being lost. Okay, you miss packets. So, yes, very similar to this. So what should we do? What should we do? What do we call this? We should do something called flow control. Flow control, right? Again, one solution will be say, okay, I have a fast sender and I have a slow receiver. What's the obvious solution? Not efficient, but obvious. To guarantee that I don't lose anything. What's the obvious? Exactly. Basically, lower down the sender to the speed of the receiver. Basically, if you're moving fast, move slow so that the receiver could get them. Why is that bad, obviously? So in teaching, as if you're telling me, if I have 70 students and one of the students is super slow, in learning, then you want me as a teacher to move at the speed of that student. What will happen to everybody else? What will happen to everybody else? The other 59 students. Yeah, maybe get bored, leave the class, or basically it will be unfair to them, right? It will be unfair to them because you'll be like, what is this? It's not fair. So obviously lowering down the sender speed, lowering it down does not solve the problem because of many issues, okay? So we need to figure out a better way, and this is what we call flow control. Is how do I control a fast sender and a slow receiver? Many algorithms, many protocols out there that look into that. Okay, but I wanted to brainstorm on this before I give you the answers of all of these that are there. People have worked on them for years and years and years. I wanted you to think about how many problems we as network designers have faced over the years and how were they solved efficiently using different protocols. Okay? Very good. Long messages, again, we already talked about this. If I have long messages and I have a message cap, so what will happen? What do we do? Yeah, what do we call it? Terminology-wise, Rida? What do we call it terminology-wise? Fragmentation. Yeah, bonus point for Rida. Fragmentation indeed. So we fragment and defragment. We already talked about this. You can see all these are issues that basically networking is based on. If you actually do networking, these are things that when we look at protocols, you kind of, I remember when you talked about this. I remember when you made us brainstorm. And I love this half an hour that I did now, really allowed us to brainstorm about the issues of networking, you know, especially the design issues. And this is what's so important. Multiplexing, same thing, you know. So obviously, if I have a connection between A and B, and I have a connection, again, the same connection maybe is used between A and B and C here, and D, okay? Supposedly, whatever that connection is, without going to details. So I could use the same connection for multiple conversations, okay? So again, very similar to what we did with the telephone line, right? The telephone line, I could multiplex on it. I could use it for DSL, and I could use it for telephone. So this is what we call multiplexing. Again, group chats and stuff like these are application layer. They're not actually channel-wise. But yes, you could think about diverting it at an application layer level. But when we say multiplexing, meaning I have a channel. This is called the channel. And I'm using it to multiplex. So I have A sending to B. And I have also C sending to D using the same channel. Channel meaning, again, communication there. Okay? That's the basic idea. But yes, you could think about it at a higher level. If I'm, again, sending multiple messages back and forth using the same application, that's an application layer. So it's a very high layer. I'm talking a little bit down the layers. And again, finally, another issue. Okay, another issue is multiple path. So if I have multiple paths from A to B, so I could go like this from A to B, or I could go like this. Okay, so this is multiple paths. So therefore, how do we solve it? Typically, what do we use when we have multiple paths? What kind of algorithms and protocols? If we have multiple paths, what kind of algorithms we create? Routing, exactly, routing. So when we talk about routing algorithm, we're going to remind ourselves of this as well. So these are the routing algorithms. So again, in a nutshell, this is really what networking is all about. These are all the issues we face and how do we solve them. I gave you some headlines and how do we solve them, and we'll be talking about them more as we go on. Okay? The issue is we need to decide, Abdullah, where to go. If I have a message, the message needs to decide, should I go this way or should I go this way? And obviously in real life, we have 5,000 other ways. So that's the issue. Okay, Abdullah? Good. So let's move on.
Professor?
Yes.
But like, wouldn't that be like good because you have multiple ways to communicate? Like
Yeah, I
send
know.
a
Nobody's
message, I
saying
mean.
it's bad. Nobody's saying it's bad. I was saying we need to decide, right? Don't we have to make the decision? We need to have a protocol
Yeah.
that tells us what to do. Because the message is there, say, oh, I could go this way, I could go this way. What should I do? So therefore, I need to have some kind of a protocol algorithm to do that. That's the idea, yeah. But of course, it's a very good way. It's a good thing, of course, yeah. Okay, so again, we're looking at services. Layers can offer two kinds of services to the layers above them. Again, either connection-oriented or connection-less. So what does connection mean? Again, meaning I establish a connection. So connection is very similar to a telephone line. Again, we already talked about it in the tutorial a little bit. So a telephone line establishes a connection. Beep, I take the telephone. Beep, I dial. You open. I establish a connection. I send. You're done. I disconnect. That's what we call connection oriented. This is a service that we have. Connectionless is no, I don't establish a connection. Basically, very similar to the postal system, is messages go on different routes until they get there. Again, I gave you examples before about this, like an email. Obviously, it's connectionless. Connection oriented, maybe real-time communication like this one typically would be a connection oriented. And we'll talk about TCP and UDP when we talk about this later on, these kind of services, especially when I do TCP, transmission control protocol. We'll talk about it later on, and datagram protocol. So user datagram protocol. So we never lose data. It's more reliability, connection oriented. Reliable connection. Usually, it's when I establish connection, it's all about reliability. You know, acceptable delay, or I don't have acceptable delay. We have different variations. Let me give you some examples. It's easier. So these are some good examples of services that we offer. Again, generic. Later on, I'll talk about specific protocols when it comes to connection-oriented versus connection-less services. So when you talk about connection-less services, meaning I don't establish a connection, again, we could have, again, these are examples. Reliable message stream or byte streams. Again, what's the difference between byte and message? I'll talk about them later on, but typically byte, meaning I'm sending one byte at a time. Byte. This is what we call a byte stream. A message stream, I'm sending, as you would expect, a message stream, I'm sending what? One message at a time. So I'm sending the message itself. That's what we call message stream versus byte stream. Again, they both have their own advantages, but if it's something super real time, so if I'm moving a cursor, I'm doing stuff, that's, again, super real time. We are talking about byte stream there. It's kind of a zoomed in version of the stream. It's very detailed. I'm sending byte. If it's more at a high level, so I have pages and so on, this is what we will say it's a message stream. So if I have reliable message stream or a reliable byte stream, after I establish a connection, again, example is pages. I'm getting pages. You know, web pages, for example, HTML pages. So this is a sequence of pages. That would be a message stream. If I'm doing, for example, remote login, I could remote desktop to your computer in real time. That would be typically a byte stream. So these are good examples of connection oriented. I establish a connection and I connect to it, okay? So reliability is all about connection oriented. So when I want reliability, I talk about connection oriented, okay? And it could be unreliable as well. For example, voice over IP. Typically, it's connection oriented. Video, it's connection oriented, but I would lose a lot, right? You would see, I cannot hear you, sir. I cannot hear you, professor. You know, you would see that because there are some unreliable designs in it. Again, because we are sacrificing what? What are we sacrificing? When you get some unreliability, I'm getting an unreliable connection sometimes, but however, I'm sacrificing reliability or quality for what? In the case of video or voice communication over IP. Yes, I mean, basically delay, right? Speed. Because I'm not like, like this. No, you're getting what I get, but you're losing sometimes the packets, right? So it's about delay. It's more about delay, right? So that's what connection oriented is. Connectionless I do not establish a connection. Do not establish a connection. It could be unreliable. Datagrams, we call them. Unreliable, like junk mail, junk emails. These are unreliable. I don't care. Let me lose it. If you want to acknowledge it, could be an email that, you know, these emails that you get, which are registered, meaning you need to acknowledge it. That's more like an acknowledgement kind of an email, if you think about it. It's connectionless still, but with acknowledgement. So you acknowledge, say, Muhammad just opened your email. It's like in WhatsApp, right? WhatsApp, if you see, you know, double tick, that's an acknowledgement, right? That they read your message, the double tick, or it's blue. One, they received it. And if it's blue, they read it, right? So this is an example of an acknowledgement. Again, typically connectionless. It could be a request reply connectionless. Again, any database query, if you're doing a database query, you make a request, okay, for the database, and you get a reply. That's typically connectionless, of course. You don't typically establish a connection. You send the request to the database, and a reply comes in. Again, very similar to Googling, right? What you're doing, you're sending to the database of Google your question, and you're getting a reply. So that's a very typical, easiest example for you to remember. We call it a request reply connectionless. This is some good examples there. Okay? Very good. So some primitives, again, when we start programming, when you start programming networking, you have something called system calls, things that are very beneficial in order for you to use the networking components. Okay, we call these system calls. There are typically 5 of them, 5 primitive ones. Of course, you will have more depending on the language. If you're using Java, they will have a specific syntax. If you're using C++, another syntax. You know, if you're using a script level, PHP, another syntax, and so on. So, but at the end of the day, these are system calls that I'm calling, which are typically 5 of them. Very important. Super, super important. Pay attention. Listen, connect, receive, send, disconnect. Okay? Or send, receive, disconnect. Maybe this is the order. So you're listening. So you're waiting for a connection. That's a function. Again, these are called typically socket calls, if you know sockets. So we're talking about sockets. If you program before using sockets. Okay? So basically, I'm listening. So think about these as functions, if you know programming. So this is a method. It's a function. So I listen. I being the device that's actually connected to the network. And in your program, you would do that. Say, watfa.listen or Sarah.listen to watfa. Okay? So listen to me. So listen is a function. Think about it this way. So yes, we use these primitive system calls in order to do any networking design. Okay? So we listen. We could connect, establish a connection to a specific entity. We could send and receive, of course. Send will have the message as an input, for example. Okay? Receive, typically we're just waiting to receive. Receive because I could be listening. Why do I listen? I will listen to make sure that nobody else will be using my connection. So I'm blocking, basically waiting for a connection. And finally, I disconnect. So typically you have connect and disconnect, any connection oriented. I connect to you, I send, you receive, and then you disconnect. So this is a typical connection-oriented service. Okay? These are the primitives of a connection-oriented service. We call these system calls. We will teach you other courses where we talk about system calls. Obviously, we'll talk about sockets later on as well in another course. But these are very important for you to understand. If I want to develop a network, any network, these are the primitives that I will end up using. Okay? Any questions so far? Very good. Okay, so this is a good example. This is a good example. You could see I have a client, I have a server. You could see I connect, I get an acknowledgement, I request for data, they reply, I disconnect. You could see the flow, very simple flow. Obviously, you have an operating system, which is the kernel, the protocol stack that I'm using, the protocol stack that we talked about. We'll talk about the standards in a second. Again, obviously, you have some drivers, same thing here. And then I use system calls. You can see where I use them. These are the system calls that the client process is actually using in order to connect to the network. This is my network, okay? So system calls allows us to access the system. Again, connecting the protocol stack with the client process. Again, you have to remember, if I open multiple applications on my computer, these applications are what? Who could tell me? These applications are what? If I open multiple applications on my computer, every application is what? What do we call it in computer terminologies? It's a what?
System process.
Open Microsoft Word. It's a process. Thank you so much. Very good. Bonus point for you. Every application is a process or even multiple processes. And every process has a what? Every process has a what? What do we call it? Every process has a what? Come on.
RAM.
Does it have an IP?
Protocol.
No. Every process has a what? How do I identify a process? What do we call it?
This thing.
An ID, a PID.
And
You haven't seen a
access
PID
number.
before? No. A PID. 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 You haven't seen a PID before? Where have you seen the PID before?
So what's
The
the full
process
form of
ID.
PID?
Process ID. Process identification. Where have you seen it before? You haven't seen it before? You guys, just to clarify, you guys all are major computer science, right? I mean, computer science, right?
Yes.
No business majors here.
Yeah, we are computer
Okay,
majors.
Okay, you need to know these guys in a very foundation course. I mean, maybe high school. So obviously you've seen PID when you do Control Alt Delete. You can still see my screen. You go to Task Manager. You can see Task Manager. Okay. If you go to
Yes.
Task Manager. Okay. If you go to Details, you see PID, right? Obviously you've seen this before. You guys should have went through. I mean, this is an interface-wise. Of course, you can do it at the command prompt level, but you could see these are the processes on my computer now. You could see when log in, it's running, how much it's taking, and again, this is the process ID. And I could kill the process. I could kill it. Again, I use the exact word, by the way. Kill is a function. It's a system call. I could kill it. Again, I could say kill PID this. Obviously, interface-wise, you could right-click on it. You could right-click on it. Okay, as you could see, I could end the process tree, meaning everything connected to it. I could end the task and that specific process. But typically, what I'll be doing is calling the system call kill. Okay, so yes, you can see these are process ID. We'll be talking about port numbers later on as well, where each one of them is working. Typically, to see where each one of them is working, I need to kind of, you know what? Let me do it now, real quick. Okay, and just if you go command prompt and you say run as admin. Okay, I'm here now. If you just put net stat -ab. Okay, so you can see it actually told me, I don't know if you can see it, right? Okay, you could see this is what you're looking at. These are the port numbers that I'm using. Okay, for these specific processes. You see them? Again, most of these are TCP they're using TCP. So just to give you an idea, I mean, this is a very simple thing. I'll talk about a little bit more later on. But you have networking commands, you know, like ping and so on, to figure out where things are working. You could also, again, it will take time because it's looping. You could also do obviously IP config to actually get your MAC address and stuff like this. Config. Okay, you could do /all. If I do IP config, it could basically give me all the IP configurations and my MAC addresses, my logical address, as you could see. So you could see, because I'm using Wollongong connection. Again, this is my physical address. You could see physical address, as you could see, 6 bytes. This is called the physical address. And obviously, if I'm within a local area network, you can see these are hexadecimal. That's what we call, some people call it the LAN address, for example. And obviously, I could have also my IP address. It gives you your specific IP address as well. Okay, so you can see here, these are the DNS server I'm using. You can see the DHCP server, the dynamic host configuration protocol server. So a lot of information we can get about us. You have to remember, we are a device connected to the network. Connectivity implies some kind of addressing. And me as a device have my own address. To connect to the network, I need some kind of addressing. And typically we have the logical address, physical address. Okay, these are two addresses that we'll be using and discussing more. So what's the relationship between the service and the protocol? Again, service, as you could see, is offered within the layers. As you could see, these are offered. Again, service and interface come hand to hand, and protocols are at different stacks. Okay, so let's go ahead and introduce OSI layering stack. Okay, I'll only introduce it now and I'll stop. So this lecture, I'll be teaching it over 2 weeks. So I started it today, a major part of it today, but I wanted you to spend the first part taking my time with it. And next week we will finish it. So you'll be only required to know up till what I finish now. Okay, so what is OSI? OSI is Open Systems Interconnection. Okay, ironically enough, it's developed by ISO, which is basically International Standards Organization. Basically, the organization that puts all the standards in the world. These are the ones who proposed OSI. It's very famous. These are called protocol stacks. The other one who's famous is TCP/IP, which we use. That's the one that won. This was the winner. But both of them more or less started at the same time. And both of them started at the same time. However, TCP/IP took over for many reasons that I'll be talking about at the end of the lecture next week. But we'll be teaching you both. Why? Because OSI is so important if you want to design your own network for the first time. It's basically good to base it on the OSI. However, if you want to program and do applied stuff, like hands-on networking stuff, you most likely will be using TCP/IP. Okay, so let's look at these. So what are the OSI principles very quick? A layer is created where a different level of abstraction is needed. So they came and said, you know what, I'm going to create layers. If I need more abstraction, I create a new layer. This is what they claim, quote unquote. However, this was one of their downfalls. I'll tell you later on why. Each layer should perform a well-defined function. They said, you know what, we're going to create a layer and make sure it's very well defined. Again, that's what they claimed. However, as we will see, this was not the truth. It's an international standard, yes, indeed, because ISO came up with it. They want to minimize the flow. And again, they want to make sure that the layers are not too big, meaning they're not overwhelmed with functionalities, and they're not too small, meaning they're not doing not too much. So they said, when we want to design the OSI into layers, we want to make sure that it's a perfect size. Every layer is a perfect size, does a well-defined job. It's very clearly defined, and we don't overwhelm it. That's what they said. Let's see how they did it. Okay, so what they came up with, the famous OSI came up with 7 layers that they defined as, again, starting with the bottom, maybe I should flip this, but typically the last layer is the physical layer. So this is layer 1 to 7. But if you want to imagine how it works, it's basically backwards. So the application layer is on top. I'll show you another picture. But typically you have the physical layer, data link, network, transport, session, presentation, and application. Of course, you need to memorize this, very famous. But I'll be talking about in details about how each functionality, how each layer functions. And in the coming weeks, in the coming 5 weeks, every chapter will be more or less about each one of them. So I will have a chapter on the physical layer, a chapter on the data link layer, a chapter on the network layer, and a chapter on the transport and these guys. So this is typically, if you could imagine, the next 4 weeks ahead of us, okay? In simple terms. So we'll try to cover the whole 7 layers as much as we can. Of course, in an introductory networking subject, we can't do much in details with them. So what are these layers? Let's look at them. So this is a better picture. As you can see, on one side, okay, so this is the sender. On one side, we're going down, the application layer all the way to the physical layer. On the other side, we're going up. So you could imagine that what we talked about before, my message would go like this. And as you would expect, the last layer is the application, right? It's the actual application. Like what? Give me an example. The application. The last layer is the application. Yeah?
WhatsApp, WebEx, Facebook, anything. Something like
What?
that. I think, do you mean by application, like, it's like the way of communicating? Is it like the center of communication?
I mean by the application, the actual application. What application? Networking application. Anybody? Any application, ya jama'a? I mean, give me example. Okay? Okay? Yeah, WhatsApp. I mean, browsing. WebEx. I mean, any application. So this is my application. This is the guy sending. So the protocol I'm using, again, if it's browsing, this could be HTTP, right? This is the protocol, right? HTTP, for example. And then it goes down. That's the basic idea of it. So yes, the application layer will basically come up with what you want to send, and every layer has specific functionality. So again, the layers are starting with the application all the way to the physical. On the other hand, from the physical all the way to the application layer. Okay? So basically, this is a very nice picture, which I'm going to close my lecture today with. And you need to know, this is the last slide. So basically, you could see, I have, as we said, interface, as you could see between the layers. I have protocols from one layer to another, okay, on different stacks. From one layer, this is very important. Okay, the first thing that you notice is the physical data link and network are basically hop by hop. We call this hop by hop. So for every intermediate node, I have to basically go down, go up 3 layers, and then go down again, go up, until I come to the last layer, I go up all the way. So the first thing you notice is that basically my transport upwards are not hop by hop. They're basically peer to peer. This is very important. Peer to peer. However, node by node, we only look at the physical data link layer and network layer. And I'll tell you what the job of each one of them is later on. But in simple terms, hop by hop, these 3 layers work within, when I say hop by hop, within the what? What do we call this? Do you remember? Come on. Bonus point within the subnet. Yes, bonus point for Sarah. Subnet indeed. Within the subnet. So within my subnet, we only focus on these 3 layers: physical, data link, and network. And as soon as I come to my destination, I go ahead and go all the way up to my application. So we don't care basically on what is the application here. We don't care. Why would we care, right? Our job is simply to basically store, what do we call it? Store and, what do we call it? Store and, bonus point, store and, come on, store and, not send, not transfer, so store and,
peer to peer.
No, store and forward. Thank you so much. Store and forward. Okay, so store and forward is basically what this is. Everybody's storing and forwarding. So the physical layer is obviously for communication purposes. We talk about it, bits and signals. The data link layer is in charge typically of error correction, typically, and other stuff, and MAC meaning medium access control, having access to the medium. And the network layer, as you would expect, is in charge of routing, meaning picking the best path, especially if I have multiple options. So these are kind of the major jobs of